1, 2, 3, sync. All right, good morning.
Good morning.
Good morning.
Morning.
Morning. Rabble, rabble, rabble. Rabble, rabble. All right, how we doing?
Good.
Who here's got senior design? Okay, oh, just a couple, just a few of you.
Just all
Just a few.
of us.
Okay, so you all have your senior design expo next Thursday, right?
Yes.
Okay, so there will not be any required lecture that day, okay, just so you know, okay? All right? I'm not a monster, okay? Yes,
Is
question?
there gonna be a supplementary lecture like I did for the snow days? Or?
Do you like it?
No, I was just curious. Just curious how much catch up we have to play.
So, we'll call it a bonus lecture, how about that? For fun.
Sounds cool.
Fun.
This isn't an April Fool's Day prank, is it?
I would bet. I have a moratorium on April Fool's Day pranks here, so no, it's not an April Fool's. Good news! April Fool's, no.
Just kidding, you guys have an exam.
Yeah. No, not an April Fool's Day prank, okay. I think the best thing would be to do, because we have a lot, you got a lot of different control methods that you have in lectures. Today, so what I'll kind of build up to what Thursday will be then, okay, next Thursday. Number one, a reminder, okay, last lecture, thank you all for coming. We got to individually go through all your projects and set up expectations for your project dynamics drafts. They are due next week on Tuesday. The lecture is up from what I talked about last week. If there's any questions about that. I know some people have conflicts and they asked to be excused for last week. I understand. If you want to have individual feedback, come see me. All right, I'm happy to do that on your projects. All right, on your project proposals. So that's order of business one. Okay. In terms of topic for today, here's what I want to cover. Okay, because so much of this course is about control. Okay. But so much of this class, for control, we need to know what we're controlling, those dynamics, okay? We would put them in state space form, right? I give you a bunch of differential equations. You put them in state space form. You can then simulate them with ODE 4.5 or Euler's method. You can give those equations to a model predictive controller or something. You can give them to a trajectory optimization. Those are all nice. But who has been giving you those original differential equations? This guy, me, thank you, yes, me, this guy. I've been giving them to you, right? Or for your projects, you have to find them or get them yourself, right? And now, many of you are mechanical engineers, and we love our non-mechanical engineering guests, okay? But dynamics can come from all, dynamics come from all different disciplines. You know, in our original homework, we had a chemotherapy dynamics, right? It became an ordinary differential equation, right? Electrical engineers will have all kinds of circuits which the charge will flow per a differential equation. And as mechanical engineers, we have all kinds of things, all kinds of systems that are governed by differential equations. Mechanical systems tend to be ordinary differential equations. Fluid systems can have partial differential equations that you're trying to solve. Who here has taken a course in PDEs, partial differential equations? Anybody? You have, a couple people. Are they more or less fun than ODEs? It's up to you, there's no wrong answer.
Depends on perspective.
Okay, what is your perspective?
Less.
Less fun. Why less fun?
They can get more complex, like Schrodinger's equations and stuff.
Oh my goodness, they can get more complex, like Schrodinger's equations and stuff. You know, whew, they get tricky, right? Now, in our course, we deal primarily with ODEs, hence the ODE 4.5, right, that we're solving, right? So, what I want to take at least some of this class to do is to give you, predominantly mechanical engineers, or the mechanical engineering curious among you, more tools to come up with the dynamics of systems that you might want to control. And technically, yes, I will be applying them to mechanical systems, but these fundamentals of how you apply these equations can be applied to other systems as well. I'm being a little vague, but what I'm talking about is we're going to be covering multi-body dynamics, okay? So today, and that is not a joke, all right? Multi-body dynamics. This will be multi-body dynamics week. It's like Shark Week, okay? Multibody dynamics.
You know it's bad when they start calling shark tooth multibody.
That's when we know we've won, okay? We've won, the engineers have won multibody dynamics, okay? And particularly, we're gonna be covering something we call, and I'll put in the parentheses for these here, rigid multibody dynamics. And the tool we're gonna use is Lagrangian mechanics, okay? Who here has covered Lagrangian mechanics before? Anybody? So it's gonna. So would people be offended by covering Lagrangian mechanics? Don't tell the professor yes, I guess, right? Okay, right. So people have not seen this. Okay. So who here has heard of Newtonian mechanics or Newton? Right? Come on, everybody. Yes, yes, yes. Newton. You know. So basically, recall Newton's second law. Okay, where you have the sum of the force vector is equal to the mass times the acceleration vector, right? F equals ma. F equals ma, good equation. Well, you're raising the roof, but the roof came down on Newton in the form of fruit,
Yes.
right? Okay, that's right. Okay? So the story goes. I don't know how true that is. I have to do a deeper dive on Newton and the apple. I think he just made that up. But anyway, so we all know F equals ma. It is true for rigid body systems, okay? That, you know, I put net forces on this pencil or this Apple Pencil or whatever, and it accelerates. And you might think, hey, that's all I need to know for rigid body systems. F equals ma. And technically speaking, it is enough to figure out how systems move. F equals ma, right? So, however, so that means let's do an example, right? Well, like a half example, what kind of motivating example? And I'm very sorry, it's going to be a pendulum. I'm very sorry. Right? So if you have a pendulum, right, and it's got some center of mass here, right, and it's under gravity. How will we come up with the equations of motion for this pendulum using Newtonian mechanics? Well, there are a couple ways, all right? The way we've done it is summing the torques about a point on that rigid body. This is a rigid body. Right? You could sum up all the torques. That's how we get that theta dot is equal to minus g over L sine theta. Okay? And specifically, the L here is going to be the length of the center of mass. So maybe we'll just put the little ball at the end. Make it a little easier, right? Okay? That we get our theta doubled out, where theta is the angle from the vertical, right? Okay? You could also sum all the forces on this mass here. Call that mass M. We could sum all the forces on that single mass in a free body diagram. Summing all the forces in the x direction, where x is horizontal, let's say y is vertical, is equal to mx double dot of t, your acceleration in the x direction. Hope we're comfortable with that at this point, right? And we could make it equal to all the forces in the x direction. Oh, so for this, it's helpful to have a free body diagram, wouldn't it? Right? So let's sum all the forces on this. So let's do a free body diagram, sum all the forces. What forces are on this little pendulum, Bob? Any forces?
Gravity.
Gravity, a good one. One of my favorite ones. Gravity is neat. Just ask Newton. Any other forces?
Tension.
Tension. We'll call that tension vector here, just to make it clear it's a vector, right? Okay, those are your forces, right? So, that's true. So if you wanted to find the acceleration in the x direction, we would say is equal to whatever x component of mg there is, there isn't, and we would say, oh, the tension force, dot product with the I hat vector, the horizontal x vector. That'll give us that component, right? Okay. But you would have to solve for whatever that tension force is. What is the job of that tension force? In your own words, what's that tension force doing?
Keep the ball from flying away.
Keeps the ball from flying away. Keeps it from swinging. Keeps it swinging in a circle, right? Okay. So we'd have to solve for that tension force this way. It's a little sloppier, but you can do it. You can absolutely do it. And we can, and perhaps we'll do it next Thursday. Okay? Okay, now, so you can use Newtonian mechanics to solve this. All right? Now, so this is called, we'll call that just a single pendulum. Okay? Now let's do another example, which would be a double pendulum. Okay? Where you've got pendulums swinging from a ceiling. Okay, and let's say you got a center of mass there. Then you have another center of mass there, all under gravity, right? Let's say you wanted to come up with the equations of motion using Newtonian mechanics here. How many bodies do we have?
2.
2. We got 2 of them, right? So we have the sum of forces on each of them. Okay? On each of those 2 bodies. And they're going to have tension forces between them, right? Every time you add a new body, there's a tension force. You have to solve for that tension force somehow. And that tension force is going to have to keep it constrained to the other body, so they're swinging like pendulums. So you end up having this process where you have to solve for all these tension forces, for all these interconnected bodies. Now, let's extend this to a 6-link pendulum, a 6-link pendulum. And you might say, Christian, are you some kind of monster? Do such things exist? Why, yes, I'm glad you asked. They do. Okay? They exist in factories. A robot arm in a factory, okay, is got a pretty normal, sort of state-of-the-art, and even kind of old at this point, robot arm. A lot of them are going to have 6 degrees of freedom. Gesundheit. Gesundheit. Right? Now, it's not necessarily exactly a 6 pendulum thing. It's a little complicated. But the idea is that, if you want to be able to move your arm in 3 dimensions, translationally, and rotate the thing you're going to pick in place in 3 different axes, roll, pitch, and yaw, that's 6 degrees of freedom, right? So you have 6 bodies that are rotating in different ways to make that move, right? So if you wanted to come up with the equations of motion for that, you're going to, using Newtonian mechanics, you're going to be solving for all these forces that are their only job is to figure out how they stay connected to other bodies. A lot of nonsense you got to do. It's actually pretty tricky. Okay? And in a lot of mechanical systems, there are a bunch of joints connected to other joints. So what if there was a better way to come up with those equations of motion? Okay? And there are multiple. So one thing I want to impress upon you is that while you might think in your mind that mechanics was solved with Newton, okay? To this very day, we are innovating faster and better ways to solve for these equations. To this very day, okay? It's actually never been probably a hotter field right now because people are trying to figure out ways to compute these equations faster on graphics cards. Why do you think that is? Any guesses? Video game's a big one. That's a real big one. Also, people are figuring out how to not only put video games on graphics cards, people are figuring out how to do artificial intelligence training, reinforcement learning training of robots in computer simulations. And they will spin out, like, on a graphics card, they will simulate 1,000 robots. Okay? So people are finding ways to execute these equations faster, better on a graphics card so that way they can train robots better. Like, these are like the YouTube videos you're seeing coming out almost every day now out of various humanoid robotics companies. Okay? So My point being is that there are lots of ways to reformulate F equals ma. And some are really fascinating and really useful. So that way your simulations can run faster on your computer. That's a big one. They can go into your control methods. You know, we were putting our dynamics into our MPC controllers. You all saw that when we coded it up over the last 2 weeks. And by the way, if you skip to the end of the last lecture, remember I showed you that video of the drones, you know, zipping around Zippy-Doo and showing where they want to go? We did that. All in class. Pretty cool. All right. So anyway, my point being, those dynamics go into all kinds of things, right? So what we're going to learn here is sort of like the next, let's call it like, I don't know, what's a good analogy? Like Newtonian mechanics, you learn that in high school when you take high school physics, right? This is like your world opening to the grand different ways that you do mechanics and dynamics, okay? And that's going to be Lagrangian mechanics. Okay? In particular, we're going to get to something called the Euler, Lagrange equations. Okay? All right. And we talked a little bit about Lagrange multipliers and things like that way back in the class in a way that was not affected any of your assignments or anything. It's just interesting. But the difference between how Newton works, Newtonian mechanics works, and Lagrangian mechanics works, put really simply, is that in Newton's method, you are summing what?
Forces.
The forces. Right? You're summing the forces, and it gives you M. Perfect, yes. I saw a fist bump over that answer. Well earned. Okay? Newtonian mechanics, fist bump. I'm sorry, forces. Sorry. Lagrangian mechanics, energies. Energies. We all know conservation of energy. We all understand this fact. Okay? So let's write this down. So Newtonian, you sum forces and Lagrangian, you sum energies. Okay? We're talking your kinetic and your potential energies, your positive, negative works, those kinds of things, right? Okay? And what you're going to, so what you're going to want to do in Lagrangian mechanics is take a look at your system and then come up with equations that represent all of your energies. Okay? So, and then you're going to apply them to an equation slightly more complicated than F equals ma, but one that actually extends very nicely to many, many degrees of freedom in your mechanical systems. Okay? So, let's do some quick examples, really quick examples here. So let's do a Newtonian We're gonna build this up from an example. We're gonna try to show you how these things work. Do a Newtonian. Let's do a Newtonian block slide. Okay, so you have a block, mass. You've seen it a bunch of times. Okay, and we're not gonna have any external forces on it yet, but that direction we'll call it x. Okay. Sliding without friction. Okay. If we want to know sum of the forces in the x direction, can be equal to mass times acceleration is equal to 0. Okay. All right. Super simple, all right? In Lagrangian mechanics, block slide, let's gonna sort of beeline through these equations here, show you what they're like, okay? I'm going to sum up our kinetic and potential energies. Here we have our energies. Our potentials is 0. Call that V, it's equal to 0. Our kinetic energy, we'll call it capital T. That is sort of, the T and V are two of the ways people talk about kinetic and potential energy. Just get used to those letters. Capital T, going to be equal to 1/2 mv squared, or x dot squared, right? Okay. Then I put it into then I compute something called L, which is equal to T minus V. You know what do you think L stands for? Reminds us of Smagangian. That's right. Yeah. That's we call it Lagrangian. And then we put it in something called the Euler-Lagrange equation. Please don't panic, we'll go over it in a second, okay? Which is equal to d dt partial L partial x dot minus partial L partial x. So T minus V is equal to just 1/2 m x dot squared, okay? This is a partial derivative. So this term right here is a partial derivative with respect to x, but here I only have x dot, I should say of t, so it goes to 0. Then I look at partial L partial x dot, that's going to be 2 times 1/2 mx, and then I take the ddt of it, so it goes to some, instead of being mx dot, it becomes mx double dot. And by the way, it's all equals 0. This is going to give us mx double dot is equal to 0. That look familiar? That's what the procedure is going to look like in Lagrangian mechanics. Yes, Jack?
How do we know to take the partial with respect to x dot and x?
Oh, I wish I had done this in a different order. Okay. I'm just showing you what it's going to look like when you're doing it. Okay. Because the general, so that's what the procedure will look like. Let's do that right now, Jack. What you want, so here are going to be your steps for computing, or actually, we'll deriving, apologies, the equations of motion using Lagrangian mechanics. Okay. Number 1, you want to find out what all your degrees of freedom are. Okay? In this case, we had a block sliding around. Just on the ground, in a plane, couldn't move it any other way. 1 degree of freedom. Okay? That pendulum we had, 1 degree of freedom. When we had the double pendulum, how many degrees of freedom did we have? 2. Right? Okay? And we're going to write them as what we call generalized coordinates. Okay? Basically, just think of them as degrees of freedom, and we'll call them Q. Okay, lowercase q. So place all degrees of freedom in a generalized coordinate vector. We'll call it Q of t. Okay, it's going to have, some Q1 of t all the way down to Qn of t. Okay. You can call the things inside what you want. In our case, Jack, what was our generalized coordinate in that block slide problem?
Just x.
Just x, exactly. Now I have a quick quiz question for you. for 0 points, but brownie points, is the number of degrees of freedom equal to your number of states in state space form?
Yeah.
You were brave, but
Wrong
wrong.
numbers.
Bravely wrong. Definitely not
No.
necessarily. How many states are required for this block slide problem, assuming you care where it goes?
2.
2, as 1 degree of freedom. Thank you for your bravery, Sam. Okay? Don't confuse it with states. Okay? In fact, a good rule of thumb is that there's twice as many states as there are degrees of freedom. Yeah. Why? Well, because you have accelerations involved, second derivatives, for each of these degrees of freedom. Good rule of thumb. Okay? So, replace all our degrees of freedom. Yes, Sam?
Is the acceleration a state? I thought it was only.
Acceleration's not a state, but velocity is.
Yeah.
And
so
position is.
Isn't that another degree of freedom? Or are we not counting velocity as separate from position as in terms of?
You're thinking of states.
Yeah.
I'm talking about degrees of freedom. So, when it comes to this rigid body sliding on this table, one direction, I'm saying, this is a great thing to clarify, this is 1 degree of freedom. Has 2 states associated with it, but it's 1 degree of freedom. Now I'm moving around in a plane, people at home on YouTube. 2 degrees of freedom, 4 states, right? Good question, Sam. Glad we're clarifying this early. Glad I brought it up. How many degrees of freedom?
6.
Bingo. How many states?
12.
Bingo. 12 states. So that means that for this, I'll tempt fate. How many Q's? 6, right? So you have 6. That actually hurt. There's little sharp edges on it. Okay. But it was stylish. So you put it in your coordinate vector, call it Q. We call those generalized coordinates. All right? Number 2. Sum all kinetic T and potential V, and these are technically time varying, excuse me. Potential V energies. Okay? For our single little system, or our little block slide system, the potential energy never changed, so you can either say it's a constant, at which point it would go away when we take the partial derivative. Like math works, you know? Okay? But we had a kinetic energy, right? And calculate L of T, the Lagrangian, where L of T is equal to T of T minus V of T. For simplicity's sake, you almost only ever see this written as L is equal to T minus V. But you understand implicitly what I mean, that your kinetic energy and potential energy can vary with time, right? Just want to make that clear. L is equal to T minus V. Okay? Finally, 3. Place L into the Euler Lagrange equations. Okay? Now, there are a couple versions, so I'm going to write out a few versions. They all technically will all work as long as you include the right terms, okay? Well, here we're going to say for a conservative system, Gesundheit, meaning a energetically conservative system. You have partial, sorry, you have d dt, those are ordinary derivatives there, capital D, sorry, upright D, not capital D. As opposed to the del, L, del, Q dot. I'm getting rid of the of t's, but we all understand that Q dot can change over time, right? Okay. Minus partial L, partial Q is equal to 0. Now, Jack, I think you just got an answer to your question. How do we know that X went into that at the bottom? X dot.
That was the only element in Q.
It's the only element of Q, exactly. It was an unfair thing for me to expect you to know the way I presented it. Okay? Okay. There you go. That's the Euler-Lagrange equation for a conservative system, meaning there's no non-conservative work happening. Okay? Now, Gesundheit. If you have with non-conservative forces, it looks very similar. With non-conservative forces, d dt, so ordinary derivative, partial L, partial Q dot, is a partial derivative. Minus partial L, partial Q, is equal to tau. And V and tau are your non-conservative forces. Gesundheit. Okay? And specifically, they will be the non-conservative forces for each of the degrees of freedom. Yes, Jack?
Is the DDT like over the whole left half? Or
No,
is it
just
the
the
first
L,
one?
just the partial L.
Okay, thank you.
Yes. Meaning it's just here, the DDT. Not all around the whole thing, no, just this. Euler-Lagrange equation. Okay. All right. Now, that's with non-conservative forces. One thing that people will talk to me about the project, lots of cool project ideas. You know, some people, or one group took my suggestion, to do a roller coaster as a system. Okay, cool, neat stuff. And one of the things we talked about is adding basically having your system be basically like a cart, like a cart. But then there's additional forces to constrain it to the roller coaster, okay? Just like our tension force, right? You think that as a constraint. A way of thinking about your pendulum, I don't know why I'm using this still, it's just trauma, okay? All right? Is that this is your mass or your pendulum, right? And you can treat it as having 2 degrees of freedom, but with one constraint to keep it going in a circle, right? So the only one physical constraint. Therefore, overall, there's only 1 degree of freedom, okay? Which you've given it 2 coordinates, x and y, right? You could do the same thing with your roller coaster, where you say, here's my roller coaster. Maybe it's in the plane, so it has 1, 2, 3 with rotation, degree of freedom in the plane. And then you have a constraint saying, oh, it must be physically on this track, right? Okay, in which case, you can add a position-based constraint, okay? With position constraints, okay? There's a word for that, it's called holonomic, okay? The equations of motion are d dt, partial L, partial q dot, minus L, partial q, is equal to tau, plus J transpose lambda, where this is what we call our constraint Jacobian. And this here is called a Lagrange multiplier. Better thought of here as a constraint force. Okay, I'm just laying them all out up front. These are like the three major forms that you can use. We'll start with the easiest. But you can see how they're just variations on each other, right? So on the left, I like to think about it, on the left side I have all my conservative stuff. All right? On the right side I like to have my non-conservative forces and my constraints. Now technically speaking, a constraint can do no work. Okay? I'm standing on the ground. The constraint force, lambda, is the normal force keeping me up, right? So it's not going to do any net work on my system just by holding me here. Okay? Just like a normal force of a hill, a block on a hill. I need my block. Right? While the normal force is what's going to be accelerating this to the left, that energy is being converted from potential energy. So the constraint is not doing any net work on the system. Okay. Right? So those are the three types of those are three ways to formulate the Euler-Lagrange equation. You can go on Wikipedia and they have fancier looking ones that I think are functionally the same. All right? So let's do an example. We love examples, right?
Yeah.
We love pendulums, right?
Yeah.
I'll take it. I'll take it. Okay. Sorry. It's just because we've seen it so many times that I want to give it to you again. We just do a pendulum, do a Lagrange equation. The point is to show you, it'll give you the thing you've seen so many dang times if you do it this way with Lagrangian mechanics. Okay? Pendulum. Boom. I'm going to draw with the bob at the end. Boom. You got some angle theta of t. Boom. G. L. I heard one yawn. I'll go faster. Isn't that like how would actually be like? People have seen like Twitch stream like gimmicks. Every time someone in the chat says this, I'll have to play Mario faster. That kind of thing. Every yawn, I have to write faster. Okay. All right. Probably a terrible teaching tool. But, okay. Step one. What's our first step, friends?
Place all degrees of freedom in a generalized coordinate vector.
Put all degrees of freedom in our generalized coordinate vector. What are our degrees of freedom? Yeah, that's right, it's theta. Okay? So we got Q of t is equal to theta of t. Oh, look at that. Thank you, Pee Wee Herman voice. Okay. All right. There you go. Generalized coordinate vector. Now, 2. What's step 2?
Sum all kinetic and potential energies.
Sum?
Calculate the Lagrangian.
Yes. Sum all potential kinetic energies and compute the Lagrangian. So, our kinetic, okay, T, all right, is going to be 1/2 mv squared, right? And I'll tell you, if you have a vector, a velocity vector, there's a cool version of that. You would say 1/2 m, the velocity vector, dot product with the velocity vector. We all remember Calc 3. 1/2 m v dot v is the cool version of it that works really nicely with vectors. all right? And however, the total velocity here is going to be, it's going to end up being 1/2 m, and the velocity, or I guess the speed, is going to be the length L times theta dot, right? Squared. So it's on a circle, you have the length, you have your theta dot, that's your velocity, right? 1/2 ml theta dot squared. Your kinetic energy, okay?
Potential?
What did I say?
You said kinetic, or the,
Sure. Potential energy, already did kinetic. Semester's getting late. Okay. All right. So 1/2, sorry, is it what mg? It's going to be mgh, right? It's going to be mgh. mgh. And so, what's the height going to be? See, when it's at the bottom, it's going to, when angle is 0, height is L. So it's going to be like minus L cosine theta is what it's going to be, right? If you assume that this here is 0, see that's 0, then when it's down here, it's at minus L. When it's up there, it's at positive L. So it's going to be minus L cosine of theta. Now I'm getting rid of the of t's, but we know, right, that the theta and theta dot, they can change over time, right? And that'll be important when we take our time derivative. Just remember that, okay? Just seeing myself from a lifetime of carpal tunnel. All right. Okay. So, you have a question? No question? Any? Pause for questions. Pause over. Okay. All right. So we only have those bodies, right? So that's our kinetic and potential energy. Then we compute our Lagrangian. Okay? That means that L is going to be equal to T minus V. That means that L is going to be equal to 1/2 m L squared theta dot squared. I just distributed the square right there. Minus quantity mg minus L cosine of theta. I see two negative signs, so I'm just going to rewrite it as L is equal to 1/2 m L squared theta dot squared plus mg L cosine of theta. Okay? I have L. That's step 2. What's step 3?
Euler-Lagrange.
Euler-Lagrange equation. Did I put step 2? Good. It's called EL equation. And we'll use the first version because this one has no non-conservative forces in it. I don't have any external torques being applied to it. I don't have friction on it. Okay? Is this new to people? New to nobody. Okay. Well, sorry to review things you all know.
are you saying like knew that friction would be an external force?
Oh, no, I apologize. I apologize, everyone. All this stuff I'm doing today, is this new to people?
It's new.
Yeah.
Yeah.
Good. All right. Okay, you all are tracking very well. I was making sure. Okay. All right. Sorry to get this. I thought this was April Fool's prank. It's like, ha ha ha. We all know the Lagrange mechanics. We thought it'd be fun to see you do it and dance. Of course, you all know that friction are non-conservative forces. Of course, I would not insult you that way. Understood. Partial L, partial Q dot, minus partial L, partial Q is equal to 0. We have no non-conservative forces. Okay. All right, so we've got a couple partial derivatives here. Let's start with this one. Let's just start writing them out individually, see what terms we get. So we get partial L, partial Q. All right? And Q, in this case, is just going to be theta, right? That means we're going to say it's going to be partial theta of 1/2 ML squared theta dot squared plus MGL cosine of theta. Okay. So if we take that partial derivative, this term, I don't see no thetas. It's just theta dot. And for partial derivatives, you gotta see it, okay? I don't see it. And here, I do see a theta. So this one's gonna go to 0. This one I do see a theta. So it's gonna be equal to the partial derivative of this with respect to theta, which is going to be minus MGL sine of theta. Okay. All right. There we go. That's one term. Now let's look at partial L. Let's look at this term up here. We'll start inside. We'll do the partial L, partial Q dot. Okay? We tracking so far? Any questions? Partial L, partial Q dot. What is that? Well, it's going to be partial, or only Q dot is going to be theta dot, right, friends? Theta dot should be 1/2 ML squared theta dot squared plus MGL cosine of theta. I don't see any theta dots over here, so that's going to go to 0. I do see theta dots over here. That's going to be equal to 2 times 1/2 ML squared theta dot, otherwise known as ML squared theta dot. Okay? Now going back to this term up here, we have to now take that partial derivative, then take the ordinary derivative with respect to time. So now we said d dt, partial L partial Q dot is going to be equal to d dt of all of this stuff right up there of M L squared theta dot. That's just going to become a theta double dot, so M L squared theta double dot. Okay? So now we have these terms. I'm just going to put them in parentheses to group them up nicely. It's going to be ML squared theta double dot minus quantity MGL sine of theta, right? It's all equal to 0. That's your EL equation, right? Now let's solve this out. Let's solve this for theta double dot, okay? So that means you're going to let's keep theta double dot on the left-hand side. Negative is positive. Put it on the other side is negative. So it's going to be equal to minus MGL sine theta. I'm going to divide both sides by ML. And it's going to give me theta double dot is equal to minus G. Oh, that's ML squared. I apologize. ML squared. See that? No one called me out on it, so I'm scared. Okay. ML squared minus G over L sine theta. Does that look familiar to anyone to you? A little bit. I'd hope so at this point. Okay. All right, I'll stop with the pendulum right there. I just wanted to show you that that equation comes from a completely different formulation of rigid body mechanics, Lagrangian mechanics. Now, was that more work? Yes. For a single degree of freedom, I would say so. But let's do something a little bit more interesting. Now, we won't derive it the whole way through. But what was one of the reasons that we wanted to use Lagrangian mechanics? Multibody problems. Okay. So let's do an example of a multibody. System. Now, I didn't say anything about pendulum on a card. Haha, April Fools, I guess. Anyway, but it's actually a really good system to try this out, right? So let's give it some position x of t that you can push the cart. Okay? And we'll have some angle of the pendulum, we'll call it theta of t. And it'll be under gravity. And what we're going to do is we're going to do steps 1 and 2. And I'll show you what step 3 looks like, but we won't do it by hand. You totally can. I'll leave it for an exercise for the viewer. Okay? Multibody system. Cart pole. Right? So when you did your cart pole homework, how do you think I got the equations of motion? Lagrange mechanics. All right? All right? Okay. So, step 1. We're on our generalized coordinates, right? Okay. So, our generalized coordinates q of t. What are our degrees of freedom?
X and theta.
X and theta. X of t and theta of t. Bingo. That's step 1. What's step 2? Energies in Lagrangian, right? Energies in Lagrangian. T is our kinetic. Okay? And V is our potential. Now, you will find, this might start to get a little trickier, because the potential energy of the cart, you're smart people, you know that's 1/2 mv squared. That's going to be 1/2 x dot squared. But what's the potential energy of the bomb? You might say, well, it was the same thing we had for the pendulum, which was L theta dot squared. Yes?
You mean the kinetic? Kinetic.
Sorry, what did I say? Kinetic energy of the bomb. What's the kinetic energy of the bomb? Thank you. Yeah.
We'd have to add the velocity of the cart.
You gotta add the velocity of the cart too. The cart, when the bob is moving, the cart can also be moving. Okay. So here's a good sub-step once your system gets anywhere complicated. Okay. Cool trick. Write a vector for each mass center. And we'll call it R1 vector, R2 vector. Okay? Cool trick. So the cart mass to the mass center is just going to be x, right? And if we have I and j coordinates here, like you remember from calculus, right? We could say that, hey, R1 is equal to x I plus 0j. And what about for the bob? Okay, we'll say that's the angle here. Theta, R2, we could say, hey, it's the position of the cart, xi plus 0j, and then we're going to add the position, the relative position of the bob, right? Okay? And just doing some trig, it's going to be in the x direction, it's going to be L, so L sine of theta, right? Because when it's 0, the x position is, doesn't get budged at all. 9 degrees. No. So I, and it's to be minus L cosine theta j. Right? So I have the positions of each of the mass centers. How do I get the velocities of the mass centers? Take the derivative. Okay. And let me quickly rewrite, with respect to time, of course, ordinary derivative. I'll rewrite this real quick so we know that, hey, that R2 is equal to x plus L sine theta I plus negative L cosine theta j. Right? Okay. That means that R1 dot is equal to x dot I plus 0j, and R dot 2 is equal to quantity x dot, and then I take the derivative of this, L sine of theta. But because we're doing an ordinary derivative, we don't want to forget the chain rule. So it'll be L theta dot cosine of theta I plus, down onto the next line, quantity minus L. We have a theta inside, so it's going to be theta dot on the outside times minus sine of theta j. So they'll become positive, j hat. It's like a formula. Where are my positions of my center of mass? Write it out. What's my velocity? Take a derivative. Write it out. Now, when we're computing our energies, remember my cool trick for computing the v squared? That's v dot v with a vector? Oh my goodness. You have a nice formulaic way of writing out your velocities, a nice formulaic way of getting your kinetic energies. Okay? This works great for your kinetic energy. Translationally, if you had a inertia to your mass, if you had a rotational inertia, it would still be 1/2, inertia times omega squared, or theta dot squared. We haven't covered that in this example, but this gives you your translational component of kinetic energy. Okay? All right? Oh, and how do we compute potential energy? Well, it's nice to know the height, at least for gravitational potential energy. It's nice to know the height of the center of mass, right? What are these? Oh my goodness, it's the height of your center of mass for each of those bodies. How easy. In fact, I'm going to write T as being equal to 1/2. I guess I have lowercase m and a couple of. I'll call this M1. Oh my goodness. Yeah. So I'm going to call this M1. I'm going to call this up here, I'm going to call that M2. For the cart and the bomb. So for the cart, it's going to be 1/2 M1 V squared, or R1 dot product with R1 dot. If you forget what dot product is, you take the first element times the other first element, then add it to the second element times the second element, plus the third times the third. Continue on if you got more, if you're doing 4-dimensional spatial kinetic energies, which we will not be doing. I'm with you. Okay. And then for the kinetic energy of our bomb, M2, R2 dot product, R2. These are all operations that we learned. Will they get hairy writing them out? Pretty quickly. If only we had some kind of computer program that does all that for us. Maybe someday. That day being Thursday. Okay? There you go. Kinetic energies. Now, your V, your potential energy, and we're dealing here with gravitational potential energy. We haven't talked about spring potential energy, but that is a potential energy. It would go in there as well. I don't have it here, but that's where it would go. Okay? It's an MGH, right, for each of these bodies. So our first body is our cart, M1, M1, G times H. Now here it's 0, so we can just wipe that out. That's okay. I'm going to show you a trick. Cool trick. I'm sorry, I think they're cool tricks. Oh. Yeah, don't worry, you're doing fine in class. It's okay. It's all right. You're doing all right. Anyway, so I think they're cool. All right. So how would be if this is a vector here? Okay, and it's a column. Let's just say it's a column vector. You know, first element's the x coordinate, second element's the y coordinate. Okay, what's an operation that we could do to pull out this second element here? Okay, you could index into it like in MATLAB and say, oh, I want the second element, sir. I'm like, oh, thank you, I could do that. Yes, Jack.
You could do like R1.j.
Yeah, yes, R1.j. Okay, and I'm going to write that. So basically, you're going to do. Basically, you're trying to find the vertical component of that vector. So R1.j would give you that. Another way to write that, okay, would be it would be to do a dot product of 0, 1 dotted with R1. And these are vectors, by the way. I apologize. Little vector hats. Hat. Right? That's a dot product, right? I'm going to put a little dot here. In MATLAB, there's even easier way to set up a dot product. Or in linear algebra, I'll say. People who took linear algebra, you'll recognize this. You'd say M1G. You could say 0, 1. You could say you want 0, 1 transposed times R1 hat. Okay? That makes sense, right? This is a 2 by 1, becomes a 1 by 2. Multiplied by a 2 by 1, the result is a 1 by 1 scalar. Energies are scalars, they're not vectors. If you get vectored energy, leave the room. Think of what you've done. Okay? All right? Plus M2G 0, 1 transpose R2 hat. There's your energies. Okay? Now, L is equal to T minus V. This better be a scalar. Okay? But then, when you go to step 3, Euler-Lagrange equations, you're taking this scalar and you're taking the derivative with respect to q's, the partial derivative with respect to q, and q dot. So those are vectors. So it will give us, in the end, a vector of equations. Okay? So if you then say, do your step 3, your EL equations, what you're going to have here is a vector of partial, it's going to have ddt, I say, partial L, partial Q dot, and I should say not partial Q dot, do our first one, which is X, partial X dot, minus partial L, partial X is the first element of the vector. The second element of the vector is d dt, partial L, partial theta dot, our second generalized coordinate, minus partial L, partial theta. And that's all equal to 0 and 0. 2 degrees of freedom. 2 equations that basically show up in this vector form. If you had 4 degrees of freedom, this would be these 4 element vectors. Okay? And MATLAB will do all that for you. It can take derivatives with respect to vectors. We've taken Jacobians. We're doing all kinds of stuff in this class. Right? That gives you your equations of motion. Now, I'm not going to take those partial derivatives of L right now. I'm not a monster. But you totally can. You can sit down and do it yourself. And come up with the equations of motion of this pendulum on a cart. Okay. Now your x double dots, your theta double dots is accelerations you solve for, they'll be buried in there somewhere, right? Still got to solve for them, right? Okay? You still have that task. Well, that's okay. There are tricks for that too. All right? So, you still need to solve for Q double dot, your accelerations, in many cases, right? If you're doing ODE 4.5, you're probably solving for those accelerations, right? To simulate. Okay? You still need to solve for Q double dot in many cases. Okay. All right, and one of the easiest ways to do this is with just a little bit of linear algebra. Okay, that you want to. So what you can do is you can replace your equations for a multibody mechanical system in what we call manipulator form. Okay. One quick aside. Right now we have these zeros and these zeros up here. Why do we have those there? It's a conservative system, energetically conservative. If you didn't have them there, let's say you had some external forces you wanted to apply, non-conservative forces. If you wanted it to be on the cart, the force, guess which zero you change? The top one. So you want to apply a torque on the pendulum. What do you change? Bottom one, right? Okay, exactly. So what do you think I did for your pendulum on a cart where you're pushing on it on the cart? And a little force right there. Okay? Now keep in mind, imagine these are like 2 bodies that are connected to each other, and let's say like you have a double pendulum and you have a torque at like this joint right here. Don't forget Newton's third law, which still exists, that if you apply torque on this one, equal and opposite torque on this one. So you'd have a torque on one and negative torque on the other. Right? Just something to remember. Okay. Here we have a force and then nothing, so ignore that. But manipulator form, okay? And the idea is that you have some big matrix, we'll call it capital M, it's dependent upon Q, times Q double dot, plus some another matrix, C of Q and Q dot times Q dot plus G of Q is equal to B times tau plus J transpose lambda, okay? You can see that the taus and the lambdas, those are for your external forces and for your constraints. We haven't talked about those, but I'm just giving you the general form here, okay? This here, this matrix, is called the inertial matrix. And I'll end with a story right before we finish here. Okay, this here is called the Coriolis matrix. You've heard of Coriolis forces? People heard of that? Coriolis effects. Has to do with things that are kind of in motion, and it creates accelerations because things are in motion. Typically, people talk about firing a cannon on the Earth, and the fact that the Earth is spinning creates a weird acceleration that veers the cannon off target. Those are Coriolis forces. So this Coriolis matrix has that in counts. And this here is your gravity vector. Okay? That's a vector here. Okay? This B is an input matrix, similar-ish to the state space input matrix. It's just a convenient way to say, hey, I have these 4 input forces. How do they affect my system? They don't affect it at all? Oh, this row is zeros. Oh, this one only affects this one? Oh, this entry is a 1, you know. And that's the same as before. That's your J transpose lambda. Same thing as before. Okay? So this is called the manipulator form. And believe it or not, and so how you come up with these different matrices, believe it or not, we've done this trick already. Okay? When we had a bunch of terms and equations in MATLAB, and we wanted to find out what matrix multiplies by it, we just took the Jacobian. If you take the Jacobian of your Euler-Lagrange equations with respect to Q double dot, what pops out? This. And if you want to find all the terms that don't have Q double dot in it, take your equations, say, hey, Q double dot's 0. What's left? Oh, it's all this. Frankly, everything else. So if you wanted to compute what Q double dot was, all you gotta do is say, hey, Q double dot is equal to M inverse of Q times everything else. Nifty, right? That's Lagrangian mechanics in one lecture. Okay? I know I waved over some of the details of, but honestly, taking the Jacobian, we've done that a ton of times in class. Because this form is good to know. My story, I was going to say, for those who don't know, a few years back I was on a television program. Okay, it was called Survivor. It is a reality television program. And they drop you off on a desert island and see how you survive with a bunch of strangers. Okay, and so I applied for this show, and for some reason they thought it was a good idea to put me on there. Okay, why I still don't know, but they fly you out to Fiji, and they're about to embark on this like month-long adventure. But beforehand, they have you get interviewed by a bunch of press outlets, media outlets, and they'll ask you about yourself because they want to be able to promote the season on CBS. And I remember they were like, I got interviewed by a couple of people from different news outlets and podcasts and stuff. Then I met with the social media influencer person, and they're like, their job was to do all the Instagram stories to promote the season. And so I was literally out on the beach, and they're like, okay, Christian, make a pose. I'm like, I don't know how to pose. I don't know how to do any of this. And they're like, I don't know. Hey, here's a stick. Can you write an equation in the sand? Yes, I can do that. I wrote the manipulator form of the Euler-Lagrange equations in the sand. I'm doing Q's, and I'm stabbing double dot into the sand, and I'm trying to do, I left out the T's, but I kept going, and I was like, all right, I got this, okay, good, all right, equals 0. This is for conservative system, I made it simple. And they're like, that's great, the Instagram stories are only a minute long, could you do that, but with a shorter equation? Oh, okay, I can do that. F equals MA, there we go. All right, that's my story. So, and lecture on our coding lecture on Thursday, I want to take us through the whole process of we define a system, and then MATLAB computes all the equations for us, and we use them. All right? Thank you very much. Have a good one. See you Thursday.
And then power pose.
I almost
Flexes.
You're in care.